It's my pleasure to introduce Joel Summerfield from the University of Birmingham, who is taking our isolated decomposition class.
Thank you very much, and thank you for the opportunity to talk, and thank you for everybody for my slightly impromptu talk earlier this week. This is there's some overlap in the areas of interest, in particular. Things are going to probably look a bit boring after the previous talk because I'm going to be working only over an algebraic closed field.
Oh no!
Yeah. With some characteristics of p, either 0 or prime, and G, again, despite all of the really interesting stuff in the last one, we're back to the familiar setting of being a connected reductive algebraic group. And it's going to, similar to my other talk, it's going to act on its Lie algebra G by the adjoint action, which, you know, like this. And what we're going to consider is what I call the stabilizer, and what I'm going to define here, the centralizer. I'm aware of that, but I'm going to be calling something else the centralizer. So think of the algebra element, and then define its stabilizer, the everything in the group that sends X to itself. And the last kind of initial bit that we need is if I take some subset of the Lie algebra, define the regular elements of that subset to be all of those that have either minimal stabilizer dimension or equivalently maximal orbit dimension. So out of all of the elements of X.
Sorry, what's the superspace effect?
Oh, G, it's the Lie algebra side.
Okay, the algebra. Okay. It's good.
Yeah.
I think you probably said it.
Okay, so this kind of makes us want to consider the stabilizer dimension map. So this is going to be a map here in our case that sends the Lie algebra elements to some natural number, and the stabilizer level sets are fibers of this map. So we're going to denote them G curly bracket M, and that's going to be all elements of the Lie algebra whose stabilizer at dimension M for some natural number M. So
you don't get it. There are floats are open.
well, so the thing is due to the Chevalier semi-continuity theorem, all of these are locally closed. So they're open in their own closure, or they're an intersection of an open and a closed set. In general, they won't be actually closed entirely, but it's all nicely behaved. They're them being locally closed subsets of the Lie algebra means they kind of inherit like some nice properties from that. And this allows us to define stabilizer sheets. So a stabilizer sheet of our Lie algebra is an irreducible component, so a maximal irreducible subset of a non-empty stabilizer level set. And these stabilizer sheets, they inherit being locally closed. They're also necessarily G stable under joint action, they're K star stable, so stable under multiplication by non-zero elements of our field. And if I let S be a stabilizer sheet, then they are precisely the regular elements of their own closure. And then, well, that kind of says that the stabilizer side of things, but the item mentions the decomposition classes. And for once, the talk I gave earlier this week didn't actually define what those are. It's normally what I talk about. So in order to define those, I'm just going to do a bit more notation. So for each X in G, so our Lie algebra, we can view it as a locally finite endomorphism of the coordinate algebra of our group. And there is a locally finite analog of the Jordan decomposition or locally finite endomorphisms of this. So that then breaks down into a semi-simple nilpotent part, which you can then show necessarily are nicely well defined in our Lie algebra, so they're left invariant derivations. So this lets us define the Jordan decomposition, and then I'm going to define the centralizer again for X in the Lie algebra is all elements Y in the Lie algebra that commute with it with respect to the Lie. And when you want to go with the centralizer, you can define the double centralizer, which there's a few equivalent ways they kind of all end up equaling each other. Really, it's all things that commute with everything in the centralizer. You can also show that this is equal to the center of the centralizer as well. So, given those, the decomposition class of some element of our Lie algebra is denoted J G of X, and I did actually tell someone the J does not stand for Joel. I didn't name these. It stands for Jordan, from Jordan decomposition, and this is all Lie algebra elements such that there exists a group element that does two things at the same time. So the easy bit is it takes the nilpotent part of X to the nilpotent part of Y. Now, if I then did the same thing for the semi-simple part, then what I'd actually just recover is the orbit, the G orbit of X under the joint action. And that already has a name. So what we want to do instead is send the act on it by the joint action and then take the connected component of the stabilizer and send that to the connected component of the stabilizer, the semi-simple part. What this ends up doing is clumping together orbits whose Jordan decomposition looks the same up to swapping out eigenvalues, especially if you've got a matrix, a nice matrix presentation of your group. It basically means you can, as long as you keep eigenvalues that were distinct, it means you can swap out eigenvalues and you stay in the same decomposition class. So these form a nice finite partition of the Lie algebra, so breaks it down into fairly many pieces, and we can recover them as if we take the double centralizer of our semi-simple part and take its regular elements, put back in our nilpotent part, and then take the G saturation. So this is kind of an explicit way of building them, and they are, I mean, they're obviously G stable, but they're also non-zero scalar multiplication stable, they're irreducible, and they're constructible. So they're a finite union, locally closed sets. And then the reason why I defined all of this stabilizer stuff is, and it's quite easy to show from the definitions, but stabilized dimension is constant on each decomposition class. I mean, you can see that obviously the semi-simple parts maintain, and then it comes from the fact that the stabilizer of an element is the stabilizer of its nilpotent part inside the stabilizer of the semi-simple part. And so each stabilizer level set is a necessarily finite and disjoint union of decomposition classes. And then, linking to sheets, it means that each stabilizer sheet contains a unique dense decomposition class. So decomposition classes were originally introduced as a tool to study sheets, because essentially it's kind of nice property that if you understand what something does to decomposition classes and you know how to figure out which one the dense one is, it gives you a lot of nice information about sheets themselves. Now, the talk mentions about isolated, so I'm going to define exactly what I mean by that. So we equip D of G, which is the set of decomposition classes, with the closure order. So it's the same one that you have on nilpotent orbits, in that I say something is less than or equal to another decomposition class, if and only if it's contained in its closure. Then we define, we say that a decomposition class J is stabilizer isolated if there does not exist any J prime in the same stabilizer level set that relates to it with respect to the closure order in either direction. Well, I'll make it straight. So it's stabilizer isolated if, amongst all the decomposition classes, if I look at the ones that lie in the same stabilizer level set as what I started with, it doesn't contain any other things in its closure, and it's not contained in the closure of anything else. And there's a nice so there's a nice result that we can, not too tricky to show that, so suppose J the condition class, then if J coincides with the stabilizer sheet, so all of these are irreducible, so it just suffices for it to be an irreducible, a maximal irreducible subset of whichever level set it's in. Then it's necessarily stabilizer isolated. Now, we want the converse as well. And it's one of those annoying, and there's quite a few of these around decomposition classes, where the converse might actually hold in all cases, because we haven't found anywhere it doesn't. But currently, we need some assumptions. And in this case, our assumption here, so is that so suppose n is the stabilized dimension where it lies. The assumption is that every stabilizer sheet of GM is a union of decomposition classes. And then we get the converse. And for those of you familiar with this kind of general theory, this condition only matters for the annoying cases, because it holds if for every stabilizer sheet S and any, or I guess equivalently, all X in the unique dense decomposition class, the connected stabilizer of the semi-simple part of that is a Levi-Summerfield. And this relates to the kind of properties I was talking about on Tuesday in terms of Levi subgroups are nice, mainly because parabolic subgroups are nice. And therefore, i.e., well, for example, this always holds when our characteristic is good. So if we're a good characteristic, then this is always a Levy, and therefore this condition ends up always holding. So it's not too hard to show that. And then we get this nice condition that it goes in both directions. Now, everything that I mentioned and defined has been for the stabilizer. So it all built off of the stabilizer dimension. Every single thing that I've said works if you consider the centralizer dimension. And so in particular, we consider the centralizer level sets. This time we've got square brackets around our subscript. And these are all things whose centralizer dimension is bigger than them. And then if you consider the irreducible components of the non-empty ones of these, you get centralizer sheets. And all of the results that I've said hold for both that I've said so far. Now, again, those of you familiar with the area might be thinking, hang on, aren't these the same thing? And they are if you have certain nice assumptions. If G satisfies the standard hypotheses, which I won't explain, but they're nice assumptions. I want to say originally due to Janssen. I know Janssen wrote a lot about them, but I'm not actually sure where he got them from. Then for all elements of the Lie algebra, the dimension of the stabilizer is the same as the dimension of the stabilizer. Oh, actually, and 4 equals 0. That also it essentially comes down to a smoothness condition. So actually, if you're in a characteristic 0 field, these coincide. So centralizer and stabilizer sheets, level sets, you only need the distinction when you're working outside of the standard levels. So that's why in most of the surrounding literature, these things are kind of uniformly just called sheets instead. But a lot of the work that I've been doing during my PhD is looking at the cases where we don't have the standard policies, where we need to make a distinction between the two, because there is a very nice result and property of stabilizer sheets that breaks quite dramatically the centralizer sheets. So there's a theorem originally due to Borho and Kraft in 79, 0, and then Karstenstein in 2, which says suppose P is good. You actually can have slightly weaker conditions than this. This makes it easier. And S is a stabilizer sheet. Then S contains a unique nilpotent orbit. And there's a quite nice explicit way of getting it. You take any element of the decomposition class, then to get that unique orbit, you take the induced orbit from your semi-simple stabilizer, the semi-simple centralizer up to G of the kinetic component of your semi-simple stabilizer applying to your nilpotent. This is where the stuff I was talking about on Tuesday becomes relevant, but in this case, because for assuming P is good, this is always a levy, which is why it's a bit nicer to state. It does hold more generally, you just can't write it in this nice form. And the important thing is this is just very much false for centralizer sheets. Even in good characteristics. So one, I won't go into the details, but if you consider G to be PGL2 in characteristic 2, then consider G of 1, so everything that has centralizer dimension 1, this is non-empty, but contains no nilpotents. The issue there is that essentially because the stabilizer not being smooth anymore, the dimension of the stabilizer stays fine, even in weird cases. The dimension of the centralizer increases for certain nilpotent elements, and basically the nilpotents that were here in characteristic 2, as in characteristic not 2, go somewhere else when the characteristic is 2. Their centralizer dimension increases, and that ends up having no nilpotents. So in the short time I've got left, I just want to give a kind of an insight to the example of the cases that we managed to figure out so far, because obviously now that we've got this sort of notion, it's quite natural to go, okay, can we classify all stabilizer isolated and centralizer isolated decomposition classes? So let G be a simple algebraic group type AN minus 1 with fundamental group Z over MZ, by getting this done by sort of N, and let M of N be all multisets of partitions of total size. So that's all unordered collections of partitions allowing for repetitions. So if you add up the sizes of all the partitions, you get n. So if we assume for now that P, our character square field, doesn't divide n over n, then by result of my supervisor, Simon Goodwin, and myself, which means Bacon's written, it's just too long, according to Simon, so I'm trying to make it shorter. Before that goes anywhere, there exists a bijection G from and then over EG. So this combinatorial object completely parameterizes the decomposition classes, and moreover, it's nice in the sense of the closure order is very nicely described combinatorially. We get a lot of, and things like the dimension of a decomposition class is very easy to compute combinatorially, and all the information that you want out of it. And then what I've done, I guess without my supervisor, don't but no, it's just I actually haven't got around to managing to show this bit yet, is that a decomposition class here is stabilizer isolated, given only if the corresponding multiset is just contains the partition with a load of ones, which is the same thing as saying that in this case the decomposition class is actually just zero. Well, sorry, not zero. It's the decomposition class of zero, which in this case will coincide with the center. Cases where the center might be one-dimensional here. And the second case then is this is centralized isolated, and if the theorem earlier is any indication, this will be more interesting. If and only if one of the following holds. And so turns out, well, we still have the zero decomposition class is still centralized isolated. That's to be expected. It very much lives on its own. So one case is where that is again just contains the partition with a load of n's, sorry, load of ones. You also get a few others. You also get one that just contains a single partition with a load of p's in it. And here we need the p to divide us n. Because originally p doesn't divide n over m, we need to divide n, and so this would be n over p points. And very strangely for me, because this is all type A stuff, and so usually exactly what the characteristic is tends not to affect most type A things. It matters if p divides n and things like that, but actually getting different results for specific p is rare, at least as far as I've encountered. But you actually get an extra centralizer isolated one. When p is 2, and also divides n, where it contains 2 copies of the partition with n over 2 ones. Yeah, and there's a much longer list, which I definitely don't have time to write, for the p does divide n over m case, but then again, stabilizer isolated is much nicer, and centralizer isolated has a longer list, and then some edge cases for p is 2 and p is 3, which I was even more surprised at. And all of it kind of falls out of hitting the combinatorics with a hammer for long enough, and eventually it falls out that which things have to be isolated and which things can't be. And so I'll finish with that.
Any questions?
if every non-smooth centralizer will fill that theorem.
Sorry?
Every non-smooth, not smooth centralizer will fill that theorem.
As in this one.
Yes.
I'm not quite sure answer the question. Sorry.
Well, remember you said that because of the people who the centralizer is not smooth.
Yeah. So it's here, yeah, so it's the fact that P is good here, luckily it's still always smooth. It's always smooth for semi-simple elements. So you always have the dimension of stabilized with a semi-simple element is always the dimension of the centralization is due to Borel. So that ends up behaving nicely. It's just the nilpotent bit that sometimes doesn't behave as you would expect it would. This is always, I mean, for the stabilized dimension is always the O dimension, as it were, of the orbit dimension. So that is kind of always still nicely behaved because the orbit dimension doesn't change when you mess around with the characteristics. So the stabilized dimension doesn't really change either. But the centralized dimension depends on properties of the Lie algebra that do change. For example, things like SLN, when P divides N, suddenly has a one-dimensional center as a Lie algebra. And that consequently means all of those elements now lie in every single centralizer where they might not have before. It doesn't end up actually affecting all of them, but it means that some of them end up gaining an extra dimension than what you have in the characteristic zero setting.